Jnanam Paramam Dheyam. Knowledge is supreme.
We have discussed the basics of lasers already. Now very quickly in the next half an hour, let us go through some applications that laser have in spectroscopy in particular and chemistry in general. Okay. To do that, first of all, this is what we need to believe actually, because I am not really going to prove this to you. So there is this seminal paper published in 1917 if I remember correctly by Einstein, which deals with this problem of stimulated emission in great detail. So all this comes out of there, but then that will be too much for us. Let us just believe what I say, and some of these you can see yourself. See, this is your laser light, right? What is the difference between this laser light and the light that comes off out of these lamps? First thing you can see is intensity, right? Right, very bright. So the intensity is very, very strong. Second thing also, what is the color of this light that you can see? It is too bright actually. What is the color? Green. What is the color of light coming out of this lamp? White. So this is highly monochromatic. That is the second thing. So essentially what happens is the emitted photon, the photon that comes out as a result of stimulated emission has exactly the same properties as the photon that causes the stimulated emission. That is what leads to all these properties. Monochromaticity and then intensity, of course, because you are building up the gain. Pulsed operation we have discussed already in the previous module, and the last part is coherence. What is the meaning of coherence? Same frequency is monochromaticity. That's why I asked that question. Same phase. What is the meaning of same phase? That they walk in steps, right? So it's like many photons marching together. Why? Because as I said earlier, you have to believe me on this for now. The output photon exactly has the same properties as the photon that comes in. And of course, if they are incoherent, of course, it would all break down, right? So they are all in phase. And these properties of each of these properties of lasers actually come handy in laser spectroscopy. Now, what I don't have on this slides is intensity. Because of intensity, what you can actually do is you can, especially in, so you can excite many molecules in using laser, right? That is what intensity does. So what you can do is, for molecules with very feeble emission, you can use a laser and still get a reasonable emission spectrum. There is an application of this in things that are as apparently far away from this course as cancer detection. See, the thing is this, all of us are emissive actually, okay. So you take any living tissue, what you have there is, you have collagen, right? Collagen is emissive. If you take paper and put it in ultraviolet light, you can see the emission, that is because of collagen. You also have proteins, right? Tryptophan, well, collagen is also a kind of protein that is emissive. And you have NADH in your blood, NADH is also emissive. But then the thing is, look at me, am I emitting light? Not exactly, right? But if I put my finger in a laser beam or a strong enough light source which is at say 340 nanometer UV, then you can see my finger fluoresce, right? Using that, people have tried to make devices even for cancer detection. Okay. One of them is right now installed in Tata Memorial Hospital in Mumbai. But we will talk about something else. As we discussed, another property of lasers is monochromaticity. Okay. You can even see it here. Qualitatively, it is green and not white. But when we say monochromaticity, it actually goes way beyond just saying that it is green or blue or red. So in the example that we discuss in the next few minutes, that is what we will try to emphasize, how monochromatic lasers can be. So first I show you a spectrum of ICL, and by the way this discussion is available in Macquarie and Simon's book. I'll show you a spectrum of ICL. Okay. First on an ordinary spectrometer. Well, when I say ordinary spectrometer, I actually am not doing justice to the spectrometer, because the resolution is 0.03 centimeter inverse, and we are talking about electronic spectroscopy. So this so-called ordinary spectrometer of ours is actually extraordinary. Okay. So in that spectrometer, which doesn't use a laser, what we get is this. This is the kind of spectrum that we get. Okay. Please look at the x-axis, 17,299.5, 17,299.6 centimeter inverse. It's actually good resolution. Okay. But see what happens when I try to record the same spectrum on a laser spectrometer. Here resolution is 3 into 10 to the power minus 5 centimeter inverse. That's why we have the audacity to call this an ordinary spectrometer, because resolution is only 0.03 centimeter inverse. Okay. There, if you look at the same range of the spectrum, this is what you get. So what you see is, these are not bands. Actually, each of these bands is made up of so many lines. Where these lines come from, we'll not indulge in a discussion of that right now. Okay. But the point we are trying to make is that because of this monochromaticity of lasers, so that is the level of monochromaticity that you can get, 3 into 10 to the power minus 5 centimeter inverse. Right. The way this has been recorded is that they have taken a laser that is tunable. So remember that L equal to n lambda by 2. So if I can change the length a little, what will happen? Instead of this lambda, another lambda will come in resonance. That is how tunable lasers work. Okay. And you can tune it so finely that you have resolution of 3 into 10 to the power minus 5 centimeter inverse. Okay. And if you thought this is good, what I will try to now show is, I will ask you to focus on this portion. I am going to blow up this portion and show you. That is what you see. Please read the x-axis now. 17,299.685, 17,299.690. Okay. There can be no other line here. See, this looks like relatively broad band. From here, we have been able to go down here by using a good laser spectrometer. Okay. So that is what the monochromaticity of lasers allow us to do in spectroscopy. Okay. Second application that we have discussed. First application is the laser induced fluorescence that we have talked about already. Now let's go over to something else. This is not really spectroscopy, this is dynamics. But then now what happens is spectroscopy and dynamics kind of go hand in hand. So one thing that chemists always want to do is, they want to control the reaction path. Okay. They want the reaction, as students of chemistry, you have studied that whenever we try to do any reaction, more often than not, we have these side reactions that give us products that are not desired, right. So the challenge of any kind of synthetic chemistry is to get the product, right, to promote the channel that leads to the desired product, and to cut out all the side products, undesired impurities you can call them. Okay. So one way of doing it is to do what we have learned conventionally. What a section of chemists and physicists have been wanting to do for a very long time is to have a fine control by which we can drive reactions in the pathway that we want it to go. And I'll take two very simple examples. Are these diagrams familiar to us? Do we know what we have drawn? So these are potential energy surfaces. You see these contours? So these are three-dimensional plots, right? This axis pointing towards you, that is the energy going up. And we have reactant on this side, we have product on this side. So since we have not studied this, so the thing is this, you have two kinds of potential energy surfaces. One, so this point, so this is called the saddle point. Okay. So saddle point, if it comes very early in the reaction path, then this potential energy surface is called an attractive one. If it comes very late, then it is called a repulsive one. And then as you are going to study in that course, for an attractive potential energy surface, if the molecule oscillates, vibrates like this, then there is no reaction, it comes back. If the molecule goes straight, then it hits the wall and then comes out oscillating in the product channel. On the other hand, in the repulsive PES, if the molecule goes straight, then it hits the wall and comes back. So it is, you don't even have to think in terms of molecules, think of some kind of a surface and you are rolling a ball up it. Okay. In this case, if the ball goes up one wall like this, then it oscillates like this and comes back. If you send it straight with enough energy, then it can cross the maximum. In that case, where the maximum comes, saddle point comes late, there what happens is this: if it goes straight, then it comes back. The only hope of getting it through is to make it vibrate like this. Okay. So it is, you have to prepare the molecule in a certain state so that it goes towards the reaction side. Okay. The only way to do it is to use a laser and what is called molecular beam. Now this we can discuss. See, when we talk about chemical reactions, many of us have done those experiments by which we have determined the rate constant, haven't we? How have we done the reaction? The reaction goes on in some vessel, right? We pipette out 5 ml, 2 ml, 10 ml, whatever it is, aliquot of the reaction mixture, put it on ice, whereby we quench the reaction and then we titrate to see how much of reactant is still left or how much of product is still formed. By that, how fast a reaction can you monitor? If you do it like that, what kind of rate constants can you talk about? So this whole process of pipetting out, putting on this ice, that takes a few seconds at least. So typically by those experiments, you can talk about reactions that require minutes and hours to get complete. But what is the fast? What happens? I mean, do all reactions take place at such slow time scales, or are there faster reactions? There are faster reactions. That brings us to a question: what is the fastest possible reaction? What is the fastest possible chemical process that can take place? And theoretically, the answer comes from this equation. Are we familiar with this equation? Eyring equation. Well, if you have not studied this, you will. Okay. So this is the rate constant. Kb is Boltzmann constant. Capital T is absolute temperature. H everybody knows. What is this Q? Partition function. Partition function. Are we familiar with the concept of partition functions yet? So this is partition function associated with the transition state. These are with the reactants A and B. Multiplied by e to the power minus EA is activation energy. Kb we know, T we know. Okay. Just believe me for now. Alright. You are going to study this in this course on chemical energetics and dynamics. Now, when can K, does K have to be large or small for the reaction to be fast? Okay. Many per second has to be there, right? So what is the maximum possible value of K that we can have? What is the maximum possible value of this exponential term we can have? 1. 1 means what? No activation energy. If there is an activation energy, reaction takes longer. If there is no activation energy, that we don't have to consider. So for putting EA equal to 0, this term becomes 1. Just believe me now that the best possible scenario is that this Q dagger by QA QB is also equal to 1. So we are left with KBT by H. Okay. This is the rate constant theoretically of the fastest chemical process that can ever take place. If you substitute the value, now everything is known. Kb we know, H we know, T we can use something like 300 Kelvin room temperature. Substitute those values, the number that comes out is 6 into 10 to the power 12 per second. 6 into 10 to the power 12 per second. So if you convert that to time, how do you convert rate constant to time? Remember what we discussed in the last, remember what we discussed last week when we talked about lifetime? Lifetime, tau is reciprocal of rate constant. So reciprocal of this rate constant turns out to be 170 femtoseconds. So the fastest chemical reaction can take place in theory in about 170 femtoseconds. Anything faster than that is in the domain of physics, we do not worry about it. Now actually it is possible to measure things that are in 10 to the power minus 18 attoseconds as well, but we do not care about attosecond. Chemists should worry about say 200 femtosecond or so if you want to study the fastest process that is there. And what is the fastest chemical process that you can think of? Yeah? What reaction? Ionic reaction? Acid base reaction? Well, acid base reaction is tempting, but then I have removed those slides. We will talk about that later if we get time. But the answer I was looking for is more generic actually, more generic than that. Breaking of a bond, some bond, I do not know which bond, but breaking of a bond is the most fundamental chemical process, isn't it? Right? That should be the fastest one. So, can we measure the time required for breaking of a bond? So, this is what gave rise to the field called femtochemistry, which started sometime in late 1970s, I believe. 1980s, 1990s were the golden era of femtochemistry, and that culminated in the Nobel Prize for Ahmed Zewail of Caltech. He is no more, he died last year or year before last, I forgot, I think year before last. But there are many other players in the field also. So, we will very briefly discuss what Ahmed Zewail had done. What we need to know at that to do that discussion is, how do you follow such fast processes? We will do at least qualitative discussion of that today and stop in 1 minute or 2 minutes, and then we will take it from there in the next tomorrow. How do you follow something that is that fast? Femtoseconds. If you remember our discussion of Fourier transform spectroscopy, time domain spectroscopy that we had in the beginning of this course, we had said that your electronics cannot give you time resolution of more than microseconds and or maybe some nanosecond. Okay? How was that problem circumvented in Fourier transform spectroscopy? So, what Manthan is saying is moving mirror setup. What, well, more fundamentally, what is it that we used to get a resolution that is faster than what electronics can get? Well, as I told you, I always look for very simple answers. What I really was looking for right now is, we use the fact that light is the fastest thing at our disposal. We use the power of speed of light. Okay? So, as we will see, we use the power of speed of light in this case as well, and since we are going to start a new discussion tomorrow I think we dedicate the entire class to this. First I will tell you a little bit about the process, and then I will tell you about Ahmed Zewail's experiments. If there is time, since you have attended me, we will talk about this mechanism of acid base reaction.